So still we are in chapter 7 and it's a live recording for soil dynamics class at BIT. So this section 7.5 is seismic loads on deep foundations. So yesterday we have seen the shallow foundations and design considerations, especially for pseudostatic approach. And we can use also softwares for other time history analysis. So for deep foundation, you can have multiple kind of deep foundation, like especially pile foundation with different configurations. You can have a pile in soft soil and with point bearing, or you can have a pile in dense soil credited for friction, or you can have piles at an angle for different purpose. And they can be loaded axially, but in seismic case, you can have lateral load also. And you can have also a compaction pile, where the pile driven and at the same time it's compacting and densifying the soil. It has a purpose, especially in liquefiable soils where it is loose. You can use this kind of piles, it's densifying the soil around it. Or you can have sheet pile walls or even piles with different configuration, like a battered at an angle, verticals, especially for offshore structures. If you have water structures like offshore drilling and that kind of structures, they have piles going to deep down in the soil or bedrock. And they usually have battered piles or diagonal piles because they have tidal waves. You have loads, either seismic loads or even tidal wave lateral loads. So the lateral loads can be resisted by this kind of diagonal configurations. And we can use this orientation of piles also for liquefiable soil. If this is soil, it's liquefiable, and usually we don't credit it, to resist the loads, but instead we may even consider to apply load on the piles, but those lateral loads can be resisted by orienting piles in different configuration. So you can go through this write-up. It's pretty much what I just discussed. And piles in general, we have two kind of forces that we usually talk in civil engineering, structural or geotech. We can have a kinematic effect, that's effect from soil. The soil can apply load on the piles. In a static design, we created the soil to resist either by friction, right? Or by passive resistance. But in dynamic case, it can liquefy. Let's say this soil is in this depths, this is liquefiable layer. Let's say you have a loose sand deposit, and to have liquefaction, you need saturation, right? You need water. There is no water in the soil. If it is completely dry, there's no potential liquefaction. Let's say groundwater is somewhere up here. So this is a potentially liquefiable soil. And the soil above may not be liquefiable, can be a good soil. But once the lower portion liquefied, then everything is acting like a semi-liquid. So it can apply lateral load on the pile itself. So the pile is, you can see it, how it's bending right here, between the liquefiable and non-liquefiable soil. Because this is like semi-liquid and this is a good soil. And there is also here, let's say this is a rock, piles are located in rock, this is liquefiable soil. So these pile portions, they are severely subject to high seismic forces from kinematic effect. This is just the soil. Now, in addition to the soil, we have the structure mass on the pile. That's what we call inertial effect. So usually you'll hear these terms. Inertial forces is from the superstructure. From the superstructure, you can have axial load, lateral load, even moment. From kinematic effect, you have the soil impact, soil loads, depending on how it's liquefiable or just a lateral motion. So we need to understand all this to design it properly. So analysis of piles under vertical load and moment. Now, similar to those designs we saw yesterday for eccentric loading, we have also similar situation here. For a static case, you may have designed this already for eccentric loads or a pile with a pile cap. You can have different configuration of piles. In this case, we have 4 of them. 1, 2, 3, 4. And let's say the CG of the pile is right here. And these piles, usually they are designed to take axial loads. And also they're designed to lateral loads. Now, similar to the static, if you have like a moment and a vertical force, net force acting on it, this is just for a static case. Assume this is, you have a lateral load, but that lateral load is coming from, it can be eccentric load, like yesterday on isolated footing, or it can be from, like from the seismic loads. Doesn't matter where it comes from. From the inertial effect, from the superstructure analysis, the structural design will give you this. You'll have lateral load, moment, vertical loads. So usually these piles are designed to take it this moment, vertical load, axial with axial configuration. So some of this, if you have a moment in this, like this, what you have is you have tension in these piles, 2 piles, and compression in these piles. So they are taking out the couple, the moment by a coupling effect. Some of the piles getting compressed, some of the other piles on the other side subject to tension load. So overall, you'll have the summation of moment 0. So if you add moments by all the pile reaction forces, it should give you a total which is applied. So you can go through this math. Load is assumed linear distribution. If you take these are the reactions and linear distribution, then these ratios are valid. P1 by D1, this is a triangle. P1, this reaction by the distance, D1, equals to P2 by D2, P2 by D2. Same on the other side. And you can solve for P2, P3, and P4 and put it back here. Then finally, you can find the reaction forces at each pile and the piles. This applies, this holds true for any number of piles. Can have 4, 6, 8, 10, whatever. This is the same as, you should be familiar with this in your undergrad study, design of foundations, or in advanced foundation design in postgraduate class. But we're going to extend this into a seismic loads. All we do is, for pseudostatic approach, the same equations will be applied. Except now the difference is the inertial forces are contributing in addition to the static eccentric loads. So that response spectrum we did in chapter 4, the corresponding peak ground acceleration or the corresponding spectral acceleration, depending on what structure you have, then you get the acceleration. Those accelerations, finally you'll get this. Either a structural engineer will give you this, the loads at the foundation level, or you could estimate it. If you assume like a single degree freedom system, like a 1-story, or the whole structure is a single mass, then you can use response spectrum. Response spectrum is assuming the entire thing is 1 degree of freedom system. Now, in general case, 2 moments in orthogonal direction you can have. We saw it in one direction, but it can be in both directions. So you can see these elevation views. 4 piles taking a cross section this way, and 2 piles a cross section this way. So it has, like, for example, 8 piles in it. So just for a static case, example 7.1, reference 3, compute max and mean axial forces for the pile shown in the figure. So the loads are given. A vertical load of 500 ton, a moment 500 ton meter, and a biaxial moment of 500 ton, and biaxial, no, the vertical force is 500 ton, but the biaxial moment is 500 ton meter in one direction, think this one is about x-axis, which is y-axis, which is this one. Then about x-axis is 250 ton meter, which is this one. So you have a axial moment and a vertical force acting on this pile cap. So N, you have 8 piles, moment about y 500 ton meter, about x 250 ton meter. You should find summation of x squared, summation of y squared. We're trying to this equation. So max compression occurs at pile 1. So you can see that, let me see, depending on the directions. Maybe my actual moment over this are not correct, should be the other side. To call it 1 is the max compression. So we are compressing 1 and this is okay. So now, which means both piles are trying to compress 1. So which pile would be subject to the maximum tension in this case? So you have a compression, a moment like this about y, and a moment like this about x. So this area is severely under compression, right? Especially pile 1. So which pile will have the maximum tension? Taddese? Now pile 1, the vertical force, the 500 ton, it will create uniform compression, right, in all piles. But the moments, they will compress one pile and they will create tension on the other side. So we know that pile number 1 will be under compression under the moments. Which pile would be under tension or the maximum tension? The answer is right in front of you. And the moods. What's that? Pile 1 is under compression. Now I'm asking the tension. Fakadu. Yeah, pile 8. That's it. So mass compression occurs at pile 1, right? Because this is the moment we have about y-axis and about x-axis. So this quadrant is under compression, right? And from this, because 1 is in the furthest side, 1 would be under maximum compression. The opposite of 1 would be 8. So what these moments are doing is they are lifting this part of the pile cap and compressing this part of the pile cap. So when they are lifting, then 8 is under maximum tension. Yeah. So compression, you can use the plus. Now for the tension, you can use minus. Fortunately, now we have tension right here, right? In some cases, you may not have depending on these values. This may be like plus 30 or something. But still, even if it's not tension, it's getting to a tension, less force. That's what I meant. So you get the idea, right? They are compressing one side, lifting up the other side. So you can find for any of number 5, 7, or pile number 6, you can find using this relation, you can find the forces in all of them. Did you study this in your undergrad? Foundation 2, I believe. Yes, right? So deep foundation, it's the same. It's just this is a static case. We didn't add any dynamic case. The only thing I'll tell you is when you consider dynamic, then the moments will be larger because you have lateral loading from dynamic. Even the vertical force will be larger too. So for the dynamic part, you will estimate that force either from software will give you or from response spectrum analysis, or you'll get it, or from just hand calculation, you can estimate it using response spectrum and assuming single degree of freedom system for the superstructure. Softwares can also do response spectrum analysis, but it will analyze the entire structure at any point considering single degree of freedom system, which is much better. You'll have global modes, local modes, they will all be considered. But for hand calculation, usually the entire structure, we're assuming it to be a single degree of freedom system. Is that clear? You'll go through it more. You'll have the material, and I'll give you the sliders, and you'll go through the numbers and the exercise. Analysis of pile under lateral loads. Now, that's previous section. This section is only for moments and vertical force. But seismic also will give you what? You will have lateral loads. And usually we don't design this connection to be fixed. There will be very large moment which will cause crack. So there will be some flexibility for some ductility. If this is too huge, we may use batter pads to take out lateral forces. So analysis of piles under lateral loads. If you have a lateral load, significant lateral loads, which is expected during earthquake, then the way we analyze it is similar to beam on Winkler foundation. You have seen like a foundation beam on soil. The soil can be represented by springs, right? Pretty straightforward. And that approach usually is called the beam on Winkler foundation. The same principle is used laterally. Now you have a pile and the soil nearby, you can represent it with the springs. At every depth, we know the G value, G increases, so we can come up with the spring values for the soil. So they may not be constant. Here they can be constant, same values. But here, spring stiffness changes with depth. Usually it can get stiffer if the soil is getting stiffer downward. So the same approach for a vertical load, beam on Winkler foundation, we can use it for pile analysis for lateral load where the soil is represented by springs. In this approach, it's called also PY approach. The PY analysis is a numerical model that simulates the soil resistance as predefined linear springs, where P is soil pressure per unit length of the pile, and Y is pile deflection. So PY analysis, if you hear the term PY analysis, that's what it is. It's similar to beam on Winkler foundation, but now since we have our pile vertical, now the springs are horizontal. And the spring stiffness can change downward because the soil usually gets stiffer. If it's shallow, you can probably assume it's same. And the springs, we can estimate them depending on the G value. They can be nonlinear. The nonlinearity is like, it may not be constant. If you remember the K value, we have been estimating theory of vibrations in the previous chapters. They are dependent on G, right? If the soil is degrading, then the G value also changes, right? So the G value, if you remember GG max curves, it's dependent on strain. So at every point, G is changing with the strain. So we can make these springs to be also nonlinear. They change with the strain or equivalent linear because spring constants are usually using the G value, right? So we have equations, we have analytical equations to develop this, and different scientists came up with different equations for springs. So the beam theory, similar to the horizontal beam on Winkler foundation, it's the same. It has a general equation, differential equation with force degree, with a soil pressure and beam deflection equation. So you can have a slope. If it's for a pile, you can have a slope or moment of the pile given by a second order differential equation, the shear force, and the pressure finally. So this is what's applied in PY analysis of pile. Basically, we are integrating this equation, find a solution, and implement it in softwares. This is not something easy to do it by hand, but there is a numerical solution for it. So pile loading, you can have pile lateral loading. It's a complicated. You can have soil springs representing the soil or the lateral pressure. And you can get net soil reaction, pile deflection with depths. You can estimate it. The slope and bending moment is two at any point. Bending moment is zero at the top, right? If you have only this, if you don't have any moment applied, that's zero. So this is implemented in softwares like LPI. The PY method consists of dividing the pile into a series of increments of equal lengths. It's being divided for each layer of springs. The soil is idealized as a series of independent nonlinear springs whose characters are represented by a PY curve. The PY curve is a pressure deflection curves. Researchers developed these curves. The governing differential equation is solved using numerical techniques such as finite difference or finite element methods. And using this, just if you have a pile to be designed for a lateral load, you can use softwares like LPile. It's a well-known geotechnical software, LPile. Because if it is vertical load and moment, you can do it even manually. But if it is a lateral load, now it gets complicated. What can cause a lateral load? Seismic can cause a lateral load. Even many other loads. It's not only seismic. If it's offshore structure in the lake, then tidal waves also can cause that lateral load. Wind can cause that lateral load. But seismic is one of them. So the PY approach is what we use if you have a lateral load. Then PY curves, they are developed by different researchers. This helps you to develop the springs. PY curves are developed account for active soil pressure, passive soil pressure, and friction resistance. So if you see it in plan, let's say this is your pile. If you take it as some section in the soil, you have active lateral soil resistance pushing the pile. And there is a passive resistance. And there is also friction, if you are considering it. Let's say you have a good soil that doesn't liquefy. So that's what LPIL is doing. It's doing all these steps at every depth. And you'll provide PY curves so it can develop the springs and analyze the entire thing. Is it doable by hand? It would be too complicated. It's really solving that fourth degree differential equation. So that's why we need the softwares. PY curves can be obtained from empirical relations or field tests. And many companies nowadays, they provide the PY curves. That's a pressure displacement relation for different types of soil at different depths. There are companies producing that, scientists producing that. So they are really available. If you don't have a field test, you can use empirical correlations. These are many of available PY curve sources. Let's say if you have in the sand soil, Rees, Cox, and COP 1974, they developed only a curve or API. Soil with cohesion and friction, Evans and Duncan in 1982. So many scientists and researchers already developed it. So you may not need to go out and do a test unless something is complicated. At least you'll get a rough estimate using PY curves from here. But if you want to be more accurate, then you'll have to come up with your own PY curves. But that's what a lateral load analysis of pile is. This LPile, that's the software I mentioned before, is a special purpose and internationally recognized computer program based on rational procedure for analyzing pile under lateral loading using PY method. The program computes deflection, bending moment, shear force, and soil response over the length of the pile. You can read more about this software. When I was a student like you, we had it like a student version of the software in a school. So we played with it a little bit. It's not that complicated. It's very easy software. It has a user manual and very easy to understand. But that's what it does. So you can analyze a pile for lateral load, and then get your reaction forces. Once you find your reaction forces, what do you do after that? You design the pile, right? Then it's the same after that. You come up with reinforcement and pile sections and things like that. And it can even a capability to analyze a pile in a sloping ground. So look for this, and you may have the software. I'm not sure. You may have the software at BIT. If there is one, just look around. It's not that complicated to understand it. For piles in liquefiable soils, the previous section was assuming the soil is good, right? But now, how about if we have a soil which liquefies? If it liquefies, then that's a different animal. You lose that soil resistance, right? It's not only losing that soil resistance, even that soil can apply huge force on the pile. So you have the inertial force from the superstructure, and now you have additional force from the kinematic effect from the soil. For piles in liquefiable soils, there are at least two methods of pile analysis commonly used: the force or limit equilibrium analysis and the displacement or PY analysis. Still, the PY method, the L-pile approach, it can do it. But now the PY curve, it uses springs, right? From the PY curves. If it liquefies, what happened to the springs? Do they get stiffer or weaker? They get weak. What's that? Weaker, yes. If you have a good soil, then if it liquefies, when it is a good soil, you have some stiffness for springs. But if it liquefies, it's turning into semi-liquid. So for liquid, like something like water, spring is very soft. You can't really depend on it. So the PY approach, what it does is it makes those springs softer. Significantly, like around 80% reduction on those springs. There will be some resistance still, but a huge loss. In the force limit equilibrium analysis, this method is analysis is recommended in several Japanese design courses for analysis of pile foundation in liquefiable soils undergoing lateral spreading. So this one, what it does is, let's say you have a liquefied stratum. Let's say this one is liquefying. Let's say this pile is, it's socketed in a bedrock. So what it does is, this is turning into a liquid or semi-liquid. Then here, we assume a lateral load from the soil, around 30% of the load, to act on the pile. And over here, the entire soil to act on the pile, the lateral pressure. 100% of the lateral pressure, here it will act on it. This is a Japanese code approach. In the liquefied zone, because it is liquid now, it is softer, so the lateral pressure is around 30%. That's what it does. You can go through this reading. So schematic sketch showing pressure distribution against the piles due to lateral soil flow associated with liquefaction. So you can see it. So we are assuming that it's laterally, it's like a gentle slope or something, or during the shaking. This is a liquefied zone, pressure from flowing soil, 30%, but the entire pressure, lateral pressure, to act on the upper layer. This is a good soil, it didn't liquefy. But now it is flowing on like a water. It's like a ship on water. So it's applying the entire force on the pile. So this is how they analyze it. So now look at it. You don't have any resistance. The pile is socketed in the bedrock, but now the kinematic impact is huge. So this pile section may be too large to design, but in this case, that's where we use battered piles. So they'll take out the lateral component. Still the inertial component at the top, you'll have all forces, vertical, moments, you design it for that. But in addition to all that, now you will design it for this additional kinematic effect. Displacement or PY analysis, this is where we use degraded springs. This method involves making Winkler-type spring mass model shown schematically in figure below. Degraded PY curves are commonly used for this kind of analysis. The North American practice is to multiply the PY curves by a uniform degradation factor of P called P multiplier, which ranges in values from zero point 0.3 to zero point 0.1. Or in average, if you take 0.2, that's like 80% reduction. In the Japanese practice, the springs are assumed to be linear elastic plastic and can be determined from elastic modulus of soil using semi-empirical formulas. The soil modulus can be evaluated from plate load test or standard penetration test. So this is what it does, that PY approach, series of springs. Now what we do is we just reduce the spring resistance by about 80% to account for liquefaction. This is like if you're doing it like a pseudo-static approach. But if you do purely like a dynamic analysis in FLAC, you'll automatically get it, which is even a better realistic approach. But it's also costly and time-taking. But you can do it both ways and compare it. You have a pseudo-static approach and then do a full dynamic analysis. Numerical modeling of pile foundation. Nowadays, complex modeling and dynamic analysis can be performed in FEM, FDM numerical modeling, Plaxis, FLAC, ANSYS, or Abacus, any of them. They can model it. But there is some limitation. How much model size you can incorporating around the pile, that's a limitation. And they can work well for a single pile, but in reality, you may have big building with hundreds of piles. So it gets too complicated. Section 7.6, Soil Spring Modeling Approach for Foundation Soil. So this last section, it's about, when we simplify the soil, we may use the springs. That's usually what structural engineers do. They don't want to make us hassle with the soil modeling, so they just simply represent with the springs. That's not a bad approach. As far as you have realistic properties for soil springs and they represent the section of the soil, even if you have like a shallow soil with rock and everything, then that's not a bad approach to approximate it. So Gazeta in 1983 summarized static soil springs, which can be used for design. And even if you design it for a static case, we know that the soil springs are dependent on shear modulus of soil, and shear modulus of soil is strain dependent for dynamic case. So the static case is when the strain is really, really low. The soil shear modulus is strain dependent, and the static spring can be reduced to account for cyclic softening due to large strain. The static stiffness of substratum foundation system for circular and strip foundation on homogeneous isotropic elastic half space. This is what Gazeta developed. For circular foundation and strip foundations, we have relations. For dynamic kit also we have relation. And because they are dependent on the G values, G is strain dependent. So depending on the strain level you're designing, we can select G values. And Gazeta also prepare the same spring approach for irregular foundation. This is like regular foundation, circular, rectangular, square, or strip. We have seen those before. He developed for irregular foundation. You can find the maximum length of that irregular foundation, 2L, and the width, 2B, and he provided relations for those. You can have any irregular kind of foundation, something like this. You can find a soil springs for those. All you do is find the maximum length, maximum width, then use Gazeta's approach. if you're going to do it, manually or like in a pseudo-static fashion. If it is software, no problem. You can put any regular foundation on the soil model, it will analyze it. And Gazeta also provided if there is rock and a shallow depths. Previous relations were assuming it's all soil, but now if you have rock at shallow depth or deeper depths, there is some correction factor for that. Assume H is the depth of bedrock, then there is a correction for the soil springs. So if a structural engineer asks you to develop soil springs, you can consider all sorts. Even if the foundation is irregular, you can use previous table. Even if the foundation has, the soil layer has bedrock in shallow depths, then you can use correction factors. You can also incorporate the G value to vary with depths. So effect of shear modulus increase with depth on soil spring, Gazeta also looked into that. So these are the equations if the G is changing with depth. You can pick one depending on what condition you are in. And finally, this is how the final model look like, at least from geotechnical perspective. You can have a distributed springs that you developed considering the site condition. You can have, let's say you are analyzing a mat foundation, and you can have the forces from the superstructure, static forces, wind or seismic, all included. And the mat then put it on elastic springs, then you can analyze this in programs. Something like StatPro or SAP can analyze. Springs can be modeled, and this plate can be modeled, and you can find your shear forces and momentus and punching shear, whatever it is in the panel. So this is like a geotechnical foundation. You can analyze it with the springs. If you are doing dynamic analysis, now the strength, the properties of the springs may vary, right? They will not be constant values. So it's going to be very tedious job. It's not going to be easy. So they are going to be non-linear. So you'll provide non-linear properties. It varies with strain. Spring and damping constant for rigid circular foundation. If you're doing a dynamic static analysis, you don't need damping, right? If you're doing a dynamic analysis, then you need damping. Wherever you have the spring, then you'll also introduce damping. If you don't introduce damping, what happens? Yeah, too much energy. So you need damping if you are doing a dynamic analysis. So that's where these damping values come. So that completes this chapter. And main reference is a reference to Brajay Madar's book, chapter 6, and reference 3, Shamshir Prakash, chapter 6 and 7. In rare cases, we use the other references, but usually it's reference 1 and 2. But depending on where it's well described, I go to the other references I provided you. You're lucky. No homework in this chapter. Okay.